Dear students, welcome to this digital lecture series. The topic of today's discussion is quantum mechanics, and in that we are going to see the Compton effect. So in 1923, scientist Arthur H. Compton, he directed a beam of X-rays of certain wavelength on a block of graphite. Now remember that graphite is nothing but a form of carbon. He studied the scattered X-rays and he observed that the scattered X-rays consist of two parts. The first part was X-rays of same wavelength as the incident X-rays, and the second part was X-rays of slightly longer wavelength as compared to the incident X-rays. Now see, the wavelength has increased. It means the frequency has decreased. So he explained that the amount of energy lost in this process, it depends upon the angle at which the X-rays were scattered. Now we have seen that the scattered radiation consists of longer X-rays, means X-rays of longer wavelength, and the original X-rays. So there was a change in wavelength between the longer wavelength X-rays and the original X-rays, and if this change was denoted by delta lambda, then this change in wavelength delta lambda, it was found to be independent of the scattering material. It was found to be independent of the incident X-rays wavelength, but it was found to be dependent on the angle of scattering. This change in wavelength delta lambda, which was nothing but the difference between the scattered X-ray and the incident X-ray wavelength. This change in wavelength delta lambda was called Compton Shift. Now, in order to explain this Compton Effect and Compton Shift, classical mechanics initially tried to explain this Compton Shift. But let's see whether it was successful in explaining it. So, what was Compton Effect? When a beam of monochromatic X-rays, monochromatic means having same frequency, means same wavelength. When a beam of monochromatic X-rays is incident on the target material of light elements like carbon or graphite, then the scattered radiation consists of two intensities peak. The first peak occurs at the original or the incident wavelength lambda, and since this is the original or incident wavelength lambda, we can also call it unmodified wavelength lambda, and the second peak occurred at slightly higher wavelength lambda dash. This was the modified wavelength. Thus, the scattered radiation consists of the original or the incident wavelength as well as some higher wavelength components also. So, this effect where the scattered radiation consists of higher wavelength is called Compton Effect. Now there is a difference in wavelength which which was denoted by delta lambda, and delta lambda is equal to the higher wavelength lambda dash minus the original wavelength lambda, and the quantity delta lambda, which represented the change or difference in the wavelength, is called Compton shift. And as I mentioned earlier, Compton shift depends. It was found to be dependent only on the angle of scattering, and it was independent of the incident wavelength and independent of the nature of scattering target material. So this is the experimental setup for the study of Compton effect. The experimental setup consists of X-ray source, which is enclosed in a lead box or lead chamber. This is the X-ray source, and X-rays are emitted in all possible directions. The beam of X-rays so obtained or so emitted, it is collimated with the help of slits to obtain a fine parallel beam of X-rays, and it is made incident on the target material. So this is the fine collimated beam of X-rays, and this is the target material, which is made up of graphite, and the X-ray beam is made incident on this target material of graphite. The scattered X-rays are collected with the help of ionization chamber. So this is the ionization chamber, and the X-rays are scattered at all possible directions. The scattered X-rays are collected in the ionization chamber, and by rotating the ionization chamber along an angular scale, the scattered X-ray radiations can be collected at different angle of scattering theta. So if you are keeping this ionization chamber along this circular scale, we can collect the scattered X-rays at different angle theta. Now the current which is produced in the ionization chamber is noted down with the help of an ammeter, and this current, it is directly proportional to the intensity of the scattered X-rays that are entering into the ionization chamber. So if we are noting the current, it means we are noting down the intensity of the scattered X-rays that are coming at a particular angle. So the Compton effect, see here, this is the X-ray, then the target material. Now the ionization chamber is kept at different angles. If this is the direction in which X-rays are emitted, then ionization chamber is in the same direction, and we are collecting the scattered X-rays at the angle theta is equal to 0. By keeping this ionization chamber along a circular scale, we can collect the emitted or scattered X-rays along different directions. So here it collects the scattered X-rays at an angle of 45 degrees. Here it is 90 degrees, and here it is 135 degrees. In each case, the current shown by the ammeter is noted down, means you are noting down the intensity of the scattered X-rays. Now a graph is plotted between the current I, means the intensity of scattered X-rays, and the wavelength along the x-axis for different angle of scattering theta. Now, it is observed when such a graph is plotted, it is observed that each graph consists of two peaks except the graph corresponding to scattering angle theta is equal to 0 degrees. If the graph corresponds to theta is equal to 0 degrees, means we are in the direction of incident X-ray only. In this particular graph, there is no two different peaks corresponding to two different wavelengths. But if you are at any angle other than 0, then the corresponding graph consists of two different peaks. Observe that for theta is here the angle of scattering. So theta is equal to 45 degrees. There are two peaks and the distance between them is very small. Now if you increase the theta is equal to 90 degrees, we still have two different peaks, but the distance between these two peaks has increased. And if you make the angle of scattering even larger, then the two peaks are there, but the distance between these two peaks is further increased. So, what can we conclude from this Compton effect experiment? The graph contains two peaks. One is at unmodified wavelength lambda, same wavelength as that of the incident X-ray, and the other peak occurs at a slightly modified wavelength lambda dash. The difference delta lambda is equal to lambda dash minus lambda. This is called Compton Shift, and it was found to be independent of incident wavelength, but it was found to be dependent only on the angle of scattering theta. And what was further observed, that greater is the angle of scattering theta, greater will be the Compton shift. Means greater will be the difference between the incident wavelength and the scattered modified wavelength lambda dash. You can also observe this in this particular figure. If the angle is 0, there is only one peak, no modified wavelength is observed. But as you increase the angle, then the Compton shift, this particular distance is called Compton shift, and it is the difference between the modified wavelength lambda dash and original wavelength lambda. This is Compton shift. Now as you increase the angle of scattering, see the Compton shift has gone on increasing. So the Compton shift depends only on the angle of scattering. Greater the angle of scattering, greater will be the Compton shift. Now, classical mechanics failed to explain the quantum shift or the Compton phenomena. Let us see why it failed. Now, according to classical mechanics, if a charged particle vibrates or oscillates with a certain frequency nu, then it will be either accelerated or deaccelerated. And if it is accelerated or deaccelerated, then according to classical mechanics, it should emit electromagnetic radiations of the same frequency nu. So what does this mean? If a charge is oscillating or vibrating with certain frequency nu, then it will emit radiations, that is electromagnetic radiations of same frequency nu. Now in Compton effect, X-rays of certain frequency nu Now remember that frequency into wavelength lambda is equal to speed of light. So if a ray is having certain frequency nu, then it is also having a specific wavelength lambda. So in Compton effect, if X-rays of certain frequency nu or certain wavelength lambda is made incident on the target material, which consists of large number of free electrons, then according to classical mechanics, the electromagnetic wave consists of the electric field vector. This electric field vector, it is oscillating or vibrating with the same frequency nu, and it is having a field around it. So now when this X-ray of certain frequency nu or certain wavelength lambda is incident on the target material, the field, the electric field, it influences the free electrons in the target. As a result, if the incident frequency is nu, then the electron will also vibrate or oscillate with the same frequency nu, means same wavelength lambda. So, if the X-rays, which are electromagnetic radiations, are incident on the target material, the electrons are influenced by the electric field and they begin to oscillate or vibrate with the same frequency nu. Now, according to classical mechanics, since the electrons are the charged particles and they are also vibrating or oscillating with certain frequency nu, then it should emit electromagnetic radiations of the same frequency nu or wavelength lambda with which they are oscillating or vibrating. Therefore, the scattered radiations, if you study the scattered radiation, according to classical mechanics, the scattered radiation should contain only one frequency or X-ray. Scattered X-rays of only one frequency means only one wavelength. Hence, classical mechanics fails to explain the Compton effect. What was Compton effect? Along with the incident wavelength, we found an increased wavelength component in the scattered X-rays. But according to classical mechanics, there should be only one component, that is the unmodified wavelength lambda. So classical mechanics fails to explain the Compton effect, and hence Compton shift could not be explained by classical mechanics. The presence of higher wavelength in the scattered X-rays could not be explained by classical mechanics, and hence classical mechanics failed to explain the Compton effect. Now, this failure of classical mechanics, it was overcome by quantum mechanics. In classical mechanics, the incident X-ray was found, it was supposed to have an electric field, electric vector, wave vector, means it took into consideration the wave nature of the light. But quantum mechanically, light is supposed to be made up of large number of particles called photons. So in quantum mechanical approach, by considering that light consists of large number of photons and these photons will interact with the electrons, which are also having a particle nature. On this concept, particle interaction concept, the Compton shift was explained by use of quantum mechanical approach. We will see it in the next lecture. So that's all about the failure of Compton shift on the basis of classical mechanics. Have a nice day.